question 2 from test 2. To approximate f double prime of -1, make sure we're all together here. Anytime you have to approximate a derivative, you just take the average rate of change on the interval where the x value is. So we're going to say f double prime of -1 is approximately equal to 0, nope, -2 minus -8 over 0 minus -2. And that's just 6 over 2. And that's just 3, which we saw in the answer before. Okay, so what I was saying is, by mean value theorem, f double prime has to equal 3 somewhere. Okay, this is just an approximation. It doesn't equal it at -1 necessarily. Okay, but it does have to equal 3 somewhere between -2 and 0. And that is by mean value theorem. But they're not asking that in this question for some weird reason. They're asking what's f prime of c have to equal 3. So because, again, we have a table for f prime, that's an intermediate value theorem question. So all we're going to say is basically, look, again, we go from -8 to -2 to 2 to 6. Yeah, it has to cross through 3, and we know that because it's twice differentiable, which means it's continuous. So I'm going to type that out because my chicken scratch doesn't look great. So since, let me see here, f of -2. So again, you just list out, hey, it's below it is -8, that's less than 3, which is less than, and you could pick any one of these other values. I'm just going to use f of 7. We'll go the whole way, which is 11. So it goes from -8, which is below 3, to 11. And f prime, well, f of x, yeah, is twice differentiable. So f prime of x is differentiable, is what that means, and continuous at least one x value where f prime of x equals 3 by intermediate value theorem. Okay, so again, you state like the conditions. Hey, it goes from below it to above it, or above it to below it, like we saw in the last question. It went from a higher number to a lesser number, a greater number to a lesser number. And you say, hey, the condition, it has to be continuous because we know it's differentiable. So IBT has to apply, and there must be some place where it equals this value. All right, so evaluate this nasty looking thing. So if you ever have to integrate f prime or f double prime or even f triple prime, however they put it, you're just going to get the derivative above that. So if we integrate f double prime, we're going to get f prime. The problem is the rule we need to use is very simple. It's this: the integral of f double prime of x dx is going to become f prime of x, right? If you had limits on here like a to b, it would be a to b. It's just the change in the antiderivative. When they start putting us all the junk around there, that's really a u substitution going on. You'll notice that this is the inside function for, they made this up, that's inside of f double prime. So to handle this, you need to let u equal x squared minus 2, which means we need to let du equal 2x dx. And we don't have a 2 in there, we have a 5. So we're going to move the 5 out front, get out of here 5. We're going to put 2 in there, which means we need to divide by 2. So that whole integral becomes 5/2 the integral of f double prime of u du. Something else to remember, so our limits were 0 and 3, but that was for x. We're switching over from u to u. So if x is 0, look right here, if x is 0, u is going to be -2. And if x is 3, u is going to be 9 minus 2, which is 7. So this is the integral we're handling. And we don't need to switch back to x now. So we get 5/2 f prime of u from -2 to 7, which is 5/2 times, and you can put it on both or just distribute later, but f prime of 7 is 11, and f prime of -2 is -8. You can see it in that table. So it's just 11 minus -8, which is 11 plus 8, 19 times 5, so that's 5/2 times 19. And what is that, 95 over 2? But again, you can leave it like this. You can leave it just like this over here too if you want to. So that's that integral there. All right, now they're making up some function g, which is this thing.
Mr. Smith?
Yeah.
Why did you have to plug in 0 and 3 into the u.
So what you could do is either, so when you switch from x to u, right, these numbers here represent x. X is going from, right over here. Well, let's just erase this. We don't need this anymore. X is going from 0 to 3, right? So when x is 0 to x equals 3. Cool. But we're switching everything over to u. There's a u in here. There's no more x's. So when x is 0, u is 0 minus 2. And when x is 3, u is 3 squared minus 2, which is 7. Does that make sense?
Okay.
So anytime you do a u sub, like, we can just do like another one real quick here. Like if we integrated from 1 to 8 of, it really doesn't matter, like sine of 2x dx. Like, you know how you would do a u sub there for that? If you put an x outside of here, let's make this a little more complicated. So like that, we'd have to let u equal x squared, which means du would have to be 2x dx, right? We'd have to put a 2 here and a 1/2 here, and this would become the integral, 1/2 the integral, of sine of u du. But it's not from 1 to 8 anymore. X was going from 1 to 8. And if x is 1, u is 1. But if x is 8, u is 64. That's how that goes, okay? And then when you're done, you don't switch back. You integrate it. So you have a 1/2. Integral of sine is negative cosine from 1 to 64. And you plug into that, okay? So it's negative a 1/2 cosine 64 plus a 1/2. It should be minus, but it's negative. Cosine of 1. Okay? So that's why that's
Okay, thank you.
all right. So they want us to find critical values of g of x and classify as maxes or mins, which means we have to derive this thing. Okay, so the function g is defined by this to find critical values, so we got to derive g. So g prime is it's going to be f double prime of that, but also we got to do the chain rule, so there's going to be a 6x squared out front minus 18x. Cool. And then we have f double prime of 2x cubed minus 9x squared. And to find critical values, we need that to be a 0. And the only way that can be a 0, remember, the whole point of factoring, this is factor, right? This is multiplied, is that either factor has to equal 0. So either that happens, right? Can we handle that? Or the second derivative of 2x cubed minus 9x squared equals 0. Now, the first one we can solve just by algebra, right? We're going to take a 6x out. That's going to leave us with an x minus a 3, right? And that means our critical values from that are x equals 0 and 3. Our critical values, so that's all together. That's all this part right here. Our critical values for the second part, we got to find when the second derivative is 0. We don't know anything about the second derivative of f, except for in the prompt, which we read very carefully, that the second derivative is always positive. And if the second derivative of x is always positive, it doesn't matter what you plug into that, it's always a positive number, which means that f double prime of x never equals 0. It cannot. Okay? So all they really want you to do is derive that 2x cubed minus 9x squared. That's all that really mattered. And find out where it is 0. So the critical values are 0 and 3. So we can write that out. Critical values are x equals 0 and x equals 3. And then he wants to tell if there's a max or min there. So relative. So the way you find local or relative max and mins is with a little number line, okay? So if we made a little number line for g prime, the numbers that go on there are 0 and 3. Remember, this part here is always positive, okay? So if we plug in something below 0, like negative 10, or negative 1, let's keep it simple, right? You're going to get 6 plus 18. That's a positive thing. Matter of fact, that's a parabola, right? So you can just, it's going to go positive, negative, positive. But if you plug a 1 in, you're going to get a negative. If you plug in something bigger than 3, like a 4, you're going to get a positive. Which means 0 is a relative max, and 3 is a relative min. So we got to write that out. And it says give a reason for your answer. This table is not a reason. You need to write it out. Okay, so let me make sure I remember this. Max at 0, yeah. All right. So there's a local max at 0 because the derivative we found. So don't say it, don't say the graph, don't say the number line. Name the function we're talking about. because g prime of x changes from positive to negative. Okay, and then by the same reasoning, there's a local min at x equals 3 because g prime of x changes from negative to positive. Okay, so that's how you answer that question. And that's so they can ask you to find local maxes and mins anywhere. Keep that in mind. That's different than them asking you if something has an absolute max or just a straight up max on a closed interval. If you see a closed interval, you've got to check the endpoints and you got to check the critical values. Okay, that's how you do that. You don't need to talk about changing sign and all that stuff. But if you don't have endpoints or they ask for local max and local min, then you got to talk about the sign of the derivative for why you know something is a local max or local min. All right. And then the last part is h of x is a solution to this, okay? Which means this y, they're trying to mess with this. This y right here is really just an h of x, okay? So h is in its own derivative. That's okay. With the initial condition that h of 2 equals negative 1. Okay, that's just 1 point. On the axis provided, sketch a slope field for the differential equation and use a tangent line. So these are separate things. Sketching a slope field, which I doubt they're going to have you do this year. All that means is go to each one of these points, which is a huge pain in the butt, and try to find what the derivative would equal. For instance, if you went to the point right here, 2, 0, right? That means you're going to
Mr. Smith,
yeah.
I think we skipped D.
I'm on E right now, aren't I?
No, D.
Use a left Riemann sum. Oh, yeah, I did. Oh, because I wrote in it there. Thank you. Okay. Well, let's do D. A left Riemann sum indicate table to estimate f of 0. Okay. So remember, if you have a point on a function, like we know f of 7 is 4, right? Then we know we can find any other value of f. So this is what f of x is equal to if we integrate its derivative from 7 to whatever value you want. Okay, so that's a big rule too. That's the fundamental theorem of calculus, basically. And again, if you don't see where that's coming from, let me know. This is an important thing here for us. Okay, we did a lot of this with rate in, rate out questions. Okay, like the value you know plus the integral of the rate of change tells you what the value is now. Okay, but they want us to approximate f of 0, which means we need to take, so f of 0 is approximately, well, actually f of 0 is exactly equal to 4 plus the integral from 7 to 0 of f prime of x dx. Okay, we can put x's in there as long as there's no x up here in this integral. So that's what f of 0 is going to equal. That's what we have to do. But that is approximately equal to, the 4 is there, plus we've got to approximate that integral. So we're going from 7 to 0, but that's also, integrating backwards is weird. So let's do this. It's actually 4 minus the integral from 0 to 7. That might look a little better for us, okay? So yeah, if you ever have to integrate from like a greater number to a lesser number, like 7 to 0, and you don't like it or you're a little unsure, just flip them and change the sign, and that way that's how you usually see it. So this is going to be equal to 4 minus, and to handle this integral, we're going to have how many subintervals should we have here? 4. Because we're going to 0, right? So we got to have this, 2, 3, 4, right? So our first interval, because I flipped the limits, we're going from 0 to 7, is 0 to 2, and we're doing a left Riemann sum here. Okay, so our first interval is 0 to 2. That's a base of 2. We're subtracting the whole integral, so it's minus this whole thing, times, since we're doing a left-hand sum, we're taking the height on the left, and that's negative 2. And it's okay if it's negative. Don't worry about the implications of that. Just take the value on the left. So I got to do. The next interval goes from 2 to 3, and the left-hand value there is 2. So it's got a base of 1 and a height of 2. Plus, I'm going to write underneath this, but so plus. The next interval goes from, 3 to 4, so that's a base of 1, and the height there is 6 on the left. Plus, the next rectangle goes a base of 3, and it has a height of 8. Okay? So that's that. And we can write that all out. We can simplify that out. I'm not going to do it. You don't have to do it. You can leave it just like that. Okay, but then also notice here, so it says
Mr.
approximate.
Smith,
What's up? Oh, this should be approximate. Yeah.
at like the table, why didn't we start at -2 to 0?
Because they want us to approximate f of 0, right? We have to start at 7 because that's the point we know. And since we want to know 0, we're just going down to 0. So the -2 doesn't matter.
All right, thank you.
Cool. A lot of times on the A/B test, they do use the whole table, but they don't have to. Just pay attention to the numbers that they're giving you. Okay? They could have had us approximate f of 3, and then we just would have gone down to 3. And that would have been 2 intervals, okay? Now, it also says determine if this is an under or over estimate. So under and over estimates for Riemann sums, there's rules for them, and we're going to talk about this later on, okay? But they're not hard. You just got to draw like a picture of this thing. So we know that f double prime is positive. So what that means about f prime is that it's increasing. Cool. And it doesn't matter what exactly it looks like. It's just increasing. It's going up. Okay. So imagine if I tried to find the area under this thing by using rectangles, right? So my first rectangle, let me switch colors. Come on, OneNote, you can do it. So our first rectangle would go from here to here. Okay, it doesn't matter what the values are. So we'd have a rectangle in here somewhere. Check this out. If I did a left Riemann sum, that means I'd take the height on the left side. Well, that's an underestimate, definitely. It's an underestimate because f prime is increasing. But if I took a right-hand sum, that'd be an overestimate. And the reason is because it's increasing. If we had a function that was decreasing, and same thing, we try to put a rectangle in there. If we took the left-hand height, that'd be an overestimate. Boom. But if we took the right-hand height, it'd be an underestimate. So because we know f prime is increasing, because f double prime is positive, I know that my estimate with the left-hand sum is an underestimate. It's going to be the rectangles are below the curve. Okay? So the only other kind of underestimates they're going to ask you to talk about are tangent lines, and if we do trapezoid rule. So while I got you here trapped, left-hand sums and right-hand sums, you tell if they're over or under, if it's increasing or decreasing. And if you're ever confused, just draw a picture of it. But the trapezoid rule and tangent lines, their over-under estimate rule is for concavity. And that has to do with this. Like if you have a curve that goes down then up again, but it's concave up the whole time, anywhere you draw a tangent line, it's going to be below that curve, right? You see this? Like no matter where you draw it, it's below the curve. So a tangent line is an underestimate if the curve is concave up. But the trapezoid rule says this, which is a little weird, but again, if you draw a picture, it's not too bad. Trapezoid rule, instead of making a rectangle on here, like a rectangle would just look like this, right? You make a trapezoid by connecting the endpoints. So if you connect the endpoints here, that trapezoid is going to be bigger than the actual area, right? The area what we want is down here, but the trapezoid has this extra piece in it. And it doesn't matter if the curve's going up or down, like it's decreasing over there, right? But if you do a trapezoid over here, it's still going to be above the curve. So the trapezoid rule is an overestimate if the curve is concave up, but its tangent is an underestimate. And then the reverse of that is true too, right? If it's concave down, the tangent lines are above it, but the trapezoids are below it. All right, so there's really 4 rules there, but if you're ever confused about it, just draw the picture. It's really easy to see that happening, okay? But because they asked us about a left-hand sum, and we know f double prime is positive, which means f prime is increasing. Again, this is an underestimate. We have less area in our rectangles than we do under the curve, and we have to write that. So this is an underestimate because f double prime of x, they told us this is positive, right? So f prime of x is increasing, and that's the function we integrated, so that's why I'm talking about this, f prime. And a left Riemann sum would underestimate. Whew. Okay, and I know we're over time here, like always. But that's fine. Again, I'm recording this. You can leave if you have urgent matters, but I'm just going to finish up part E here, okay? Real quick. So part E is saying, this is a particular solution. We already talked about this. Like all a slope field is, you go to each point and you put a little dash that has the slope that the function would have if it went through there. So for each one of these points, which is a pain in the butt, we got to plug in the x and the y values to get them. Okay, so for instance, 2, 0, which is right here, if you plug in 2, 0 into that derivative, you would get 0 times f prime of 2, right, over 2 times 2 minus 1. But 0 times anything is 0. So here, there's just a flat dash right there like that, okay? The same thing's going to happen if we plugged in 3, 0, right? These would all become 3's here. Oh, that's still a 2, right? But it's just a dash, so flat. And the same thing would happen if we plugged in 0, 0. If anyone's not sure what I'm doing, let me know. This should be a simple question too. You're really just doing some arithmetic and seeing what it equals. But all those slopes equal 0 there, okay? So that's what happens there. But if you plug in the point right here, 1, 0, 0, 1, we get 1 times f prime of 0 over 2 times 0 minus 1. Well, f prime of 0, we don't know that. We gotta look on the table up here, is negative 2. Okay, that's right here. F prime of 0 is negative 2. So that's 1 times negative 2, which is negative 2, over, down the bottom is 2 times negative 1. That's also negative 2. So that's a slope of 1. So to the best of my ability, I'm going to come over here and just try to draw a line that has a slope of 1 right there. Okay? And we're going to do the same thing at this point down here, negative 1, 0. All that changes is this y value becomes negative 1 there. Okay? Right? Because y is negative 1, 0 is still x, and that all stays the same. So you would get positive 2 over negative 2, which is negative 1. And that would look like a slope of this. Yeah, they're not going to get a rule. If they make you do this, like they're not going to get a ruler out and like measure your slopes. They're just going to see are they close to what they're supposed to be. All right. So if we do the other 2 points, like this point right here is 2, 1. I'm going to do it over here so we have some more room. So the y value there is 1, right? But we need f prime of 2 over, and again, I'm just using our derivative rule right here, 2 times 2 minus 1. Cool. And f prime of 2 from our table is 2. So it's 1 times 2, which is 2, over 2 times 1, which is also 2. So 2 over 2 is a slope of 1. I'm just going to try and make it parallel to the last one I did. Okay. Then I'm going to do the point down here, which is 2, negative 1. And all that does is change again. It makes that y negative, leaves everything else the same. So that's going to give us negative 2 over 2. So that gives us a slope of negative 1. Woo-hoo. Here we go. And then the last one we got to do is 3, 1. So we plug a 3 in. We get f prime of 3 and 3 minus 1 down the bottom. But the x or the y value is still a 1. So all I need now is f prime of 3, which they tell me is 6. Nope, here's still a 3. So we get 1 times 6 over 2 times 2, which is 4. And that's 3 halves. So that's just a little bit steeper than 1. So I'm just going to kind of make it a little steeper than the last one. Okay, you can try to aim for a slope of 3 halves. That's like down 2 or down 3, back 2 if you want to do it like that. And then if you plug in, what's the next one? 3, negative 1. That just turns this to a negative, which gives us negative 3 halves. So we'd see something like this. That's all a slope field is. You just go to each point. It's kind of annoying. You find the slope for each one, and you draw a little dash that has that slope. And the last thing they want is, this is a totally separate question. Use a tangent line at 2 to approximate 2.1. Well, they're telling me at 2, the y value is negative 1, right? So that means our tangent line is going to be y minus negative 1, that's plus 1, equals, we have an x minus 2 over here. We just need the slope. But this is the slope of h, not the slope of f. So we need h prime of 2. All right? H prime at 2, negative 1. Which we happen to find. We already found, so they kind of made us find it. They definitely made us find it on the tangent line, or the slope field. Like the point 2, negative 1 is right there. But the way you'd find the slope there, if we hadn't found it, is we'd have to use this derivative. You put in negative 1 for y, 2 for x. It'll look like that, all right? But we already did it, and we got negative 1, right? Because f prime of 2 was, what was it, 2? Yeah, was 2. So that's what, negative 2 over 2, which is negative 1. So that's our tangent line right there. And if they want you to approximate h at another x value, you just drop that x value into your tangent line. So y plus 1 equals -1 times 2.1 minus 2. Which is y plus 1 equals -1 times 0.1. It's negative. I'm going to subtract off 1, so we're going to get -1.1. So we're going to say h of 2.1 is approximately that. And that is the end of that. That's our answer right there. Boom. Well, this is our answer too, because they asked for the tangent line. Okay. Good work. Let's stop this.